Continuing with angular momentum, many engineering problems involve the moment of linear momentum of flow streams and the rotational effects that are caused by them. So such problems are best analyzed by considering or taking into account the angular momentum equation that is generated. An important class of fluid devices such as turbo machines, centrifugal pumps, meaning to say in which rotation is involved. All these are best analyzed by considering angular momentum equation. So the devices that involve rotation of the bodies, then the angular momentum equation is very useful. A force whose line of action passes through a point O produces a zero moment about the point 0. The direction of rotation m r cross f, the angular momentum will be given, in fact the vector will be given by r, the radius, times the force cross f, and its direction will be obtained by considering the right hand thumb rule that we mentioned or we discuss when we consider the vectors or vector product and so on. So similarly, the moment of a force F about this point O is the vector product of R and F, that is M is equal to R cross F, and its direction, as I said, is determined by the right hand thumb rule. As you can see, if we rotate it as R cross F in this direction, then the vector is moving in the upward direction, and with respect to the rectangular coordinates, it's like going upward in the z direction. And if we move this thing in the left hand direction, try to revolve it or rotate it on the other side, then the vector will be moving in the downward direction. But remember, the positive direction of the resultant vector of R cross F is always considered as by considering or taking into account the right hand thumb rule that we have discussed many times at various points, and the picture also shows the same thing. And you can see the resultant vector M going up in the upward direction, in the z direction, so to speak. The moment of momentum then can be written as H equals R cross M into V is the moment. So moment of momentum will be R cross M into V, that is written as this, and for the whole system it is the integral over the whole system R cross V into the rho over the whole volume. So if we integrate this integral, this will take care of the total mass of the fluid that is under consideration, or for that matter of the system. And d by ht, the rate of change of moment of momentum, is therefore equal to dh by dt, that is d by dt is equal to this integral that is given here and is reflected here. The rate of change of moment of momentum can also be expressed of summation of all these forces and summation of all the vectors that occurs in the form R cross F. And in the integral form, they can be written as R cross V into rho into velocity in the radial direction times the normal unit vector n over the area of cross section. The angular momentum equation in general form is therefore written as the total angular momentum summation of all m is equal to the integral, the derivative d by dt of the integral r cross v into rho into dv. V here is not velocity but the volume, and the same here, and plus this was over control volume, and this part is over the control system, R cross V into rho VR dot N times dA. So, the sum of all external moments, as I said earlier, acting on a control volume is equal to the time rate of change of angular momentum of contents of the CV and that of the mass flow, surface of the mass flow. Fixed CV is therefore given by, for fixed CV, the summation of all external moments are given by this equation. The angular momentum equation is obtained by replacing B in the Reynolds transport theorem that we have discussed some time ago by the angular momentum H, and by small b by the angular momentum per unit mass R cross V. So you can see this is the equation that we have from Reynolds transport theorem, and there we made these changes as we just mentioned, and we obtain this equation, which is the angular momentum equation that is derived from Reynolds transport theorem.